Earth has always seemed steady beneath human life, quiet, predictable, constant. But scientists are now tracking subtle changes that suggest something unusual may be happening to the planet itself. From shifting weather patterns and polar motion to changes measured by satellites, clocks, and observatories. The signals are small, but they are real. Tonight, this video explores what researchers are seeing, what it might mean, and why Earth may be changing in ways few people notice. If science and space documentaries help the mind slow down, like the video, subscribe to the channel, and stay with the story. Civil time begins as an agreement that a day has a steady length, and that every moment can be labelled in a single shared framework. Modern civil time rests on the atomic second, a unit built from the regular rhythm of matter. In an atomic clock, atoms of cesium-133 change energy state in a way that produces radiation of a very stable frequency. The second is defined as the duration of 9,192,631,770 periods of that radiation. This definition does not depend on sunrise, seasons, or the turning of Earth. It is a time unit that remains the same in a laboratory in winter or summer, on a mountain or at sea level, in a year of storms or a year of calm. From this steady unit, laboratories maintain a continuous stream of time. They count seconds, then minutes, then hours, and they create a scale called International Atomic Time, a uniform reference that does not bend to the changing spin of the planet. Civil society, however, also lives with an older meaning of day, the interval between two similar positions of the sun in the sky. That solar day is not perfectly uniform. Earth does not rotate like a rigid wheel turning on a frictionless axis. The planet is layered and flexible, and parts of it shift, flow, and trade motion with one another. Gravitational pulls from the moon and the sun raise tides, and the motion of those tides slowly transfers angular momentum. Over long spans of time, tidal friction acts like a brake, lengthening the day by very small amounts. Over shorter spans, many processes create small accelerations and slowdowns that add or subtract fractions of a thousandth of a second from the length of a day. The world therefore keeps two closely related kinds of time at once. One kind is built from atoms and aims for steadiness. The other kind follows Earth's rotation and aims for alignment with the sky. The rotation-based scale is called UT1. It is derived from careful observations of Earth's orientation in space, expressed as an angle of rotation rather than a count of atomic seconds. UT1 tracks the turning of the planet relative to distant objects, so that noon remains near the time when the sun reaches its highest point in the sky for a given longitude. UT1 is not a perfectly smooth line, because Earth's rotation is not perfectly smooth. Between these two scales sits a compromise called Coordinated Universal Time, known as UTC. UTC is kept close to atomic time in its moment-to-moment ticking, because it uses the same kind of second as atomic time. At the same time, UTC is kept close to UT1 because civil time is expected to remain linked to the day defined by Earth's rotation. The link is maintained by occasional adjustments called leap seconds. A leap second is a single inserted second that makes UTC match. UT1 more closely when the gap grows too large. In practice, the goal has been to keep UT1 and UTC within less than 1 second of each other. A leap second is not an attempt to change Earth. It is an administrative step that changes the labeling of time so that the civil clock does not drift away from the sun by more than a small amount. When a leap second is added, a minute contains 61 seconds. That minute occurs at a specified moment, and then the clock returns to 60 seconds per minute. The day is still close to 24 hours, but 1 minute has a different count, when no leap second is added for many years. UTC remains continuous and simple for machines, while UT1 gradually moves away from it by small increments as Earth's rotation wanders. The unusual attention described by scientists in recent years comes from the fact that the gap between atomic time and Earth rotation does not always grow in the same direction at the same pace. The long trend from tidal breaking points towards slower rotation and longer days. Yet measurements also show stretches when Earth rotates slightly faster than expected, and days become slightly shorter. In those intervals, UT1 can move toward UTC rather than away from it. The idea of a negative leap second arises from this possibility. A negative leap second would remove a second instead of adding one, creating a minute with 59 seconds. That step has never been used in civil timekeeping. It remains a concept discussed in standards bodies and timing institutions, because many modern systems assume that time steps forward in uniform increments without missing labels. The language used to describe these timescales sounds abstract, but it reflects practical needs. Navigation systems, financial networks, power grids, and communication links rely on precise timestamps. Astronomy and spacecraft tracking rely on Earth orientation. Geodesy, the science of measuring Earth's shape and rotation, relies on both. A small mismatch between UTC and UT1 has little effect on daily life, but it matters for instruments that integrate signals over long periods, and it matters for coordinating observations across continents. For a global network, a difference of even a fraction of a second corresponds to a shift in Earth's rotation angle, and that shift corresponds to a change in where Earth appears to point in space. The agreement that holds UTC near UT1 is therefore a bridge between two meanings of time. One meaning is the uniform tick of atoms, the other meaning is the turning of the planet under the sun. The bridge works because Earth's rotation changes slowly enough that small corrections can keep the two aligned. The bridge also exposes the planet's subtle variability. Each leap second decision is a statement about how Earth has behaved over recent years. Each published difference between UT1 and UTC is a measure of how the whole planet shares angular momentum among its connected parts. When scientists say something unusual is happening, the phrase can refer to this measured behavior at the boundary where civil time meets planetary motion. It is a precise observation that the length of the day is a living quantity, defined by a world that remains in motion. To see Earth's rotation as it truly behaves, scientists do not look first at the ground under their feet. They look outward to objects so distant that they serve as a nearly motionless backdrop. Across the sky, remote quasars pour out radio waves from the far universe. These sources lie so far away that, for the purpose of measuring Earth's orientation, they act like fixed points. Against that stable background, the turning of the planet can be tracked with extraordinary care. The most important observing method for this work is very long baseline interferometry. The name is technical, but the idea is simple. Radio telescopes placed far apart on Earth listen to the same quasar at nearly the same moment. Because the stations stand at different places on a rotating globe, the signal reaches one dish slightly before the other. The time difference is extremely small, yet it can be measured with remarkable precision. From many such differences, analysts determine how Earth is oriented in space and how fast it's turning at that time. This method depends on separation. A baseline is the distance between two telescopes. When that distance is very long, often stretching across a continent or from one side of an ocean basin to another, the tiny delay between arrivals becomes more informative. Each pair of stations adds one geometric constraint. A network of many stations adds many more. The data are then combined so that the orientation of Earth can be solved together with the positions of the stations and the positions of the radio sources. The planet's rotation angle emerges from this web of measured delays. The telescopes do not work alone. Each site keeps time with highly stable clocks so that the recorded signals can later be aligned. In practice, hydrogen maser clocks provide the needed stability for the observation itself. The raw recordings from different sites are brought together and correlated, meaning that their patterns are compared in detail until the tiny time offsets become clear. Those offsets are not interpreted in isolation. Analysts must also account for the path that the radio waves take through the atmosphere, the exact positions of the observing stations, the motion of tectonic plates, the loading of the crust by air and water, and small changes in Earth's axis direction. What appears to be a simple timing problem becomes a careful reconstruction of the geometry of a moving planet. Very long baseline interferometry has a special place in this work because it ties Earth directly to a celestial reference frame built from distant extragalactic radio sources. This is why it is the primary technique for determining UT1, the time scale that follows the actual rotation angle of Earth. Other observing systems are also essential, but they support the full picture in different ways. Satellite laser ranging sends brief laser pulses to satellites equipped with reflectors and measures their return time. Global navigation satellite systems provide continuous signals from constellations in orbit, revealing station motion and changes in Earth orientation through precise tracking. DORIS, a radio tracking system that uses ground beacons and satellites, adds another source of geometric information. Together, these methods strengthen the terrestrial reference frame, the stable map of station positions on Earth from which orientation changes are inferred. The measurements themselves do not become official time information until they pass through institutions built for this purpose. The central coordinating body is the International Earth Rotation and Reference System Service, known as IERS. It gathers and combines Earth orientation data from several technique services and product centers. Within this system, different centers focus on different tasks. Some concentrate on rapid estimates for operational needs. Others produce more carefully refined values after more observations and checks have been completed. This division reflects the two demands of modern geodesy and timekeeping speed and reliability. A rapid estimate is valuable because navigation systems, satellite operations, and observatories cannot wait long for information. If Earth's rotation shifts even slightly from prediction, models must be updated. For this reason, IERS maintains a rapid service and prediction center that issues frequent values for polar motion, UT1-UTC, and related quantities. These rapid products allow users to work with the best available estimate in near real time. Later, as more observations are collected and combined, final values are published with greater stability. The difference between rapid and final data is not a contradiction. It is the ordinary path from first measurement to mature record. In this framework, standards matter as much as instruments. The telescopes, satellites, and clocks must all be interpreted within common reference systems. One reference frame fixes directions in space using distant sources. Another fixes positions on Earth using observing stations whose coordinates are maintained and updated. Earth orientation parameters then connect the two. They describe how the terrestrial frame turns and shifts relative to the celestial one. Among these parameters, UT1-UTC expresses the difference between Earth-based time and the civil atomic scale. Without agreed standards for frames, models, and processing conventions, the observations from different techniques and countries would not fit together cleanly. The published values therefore carry more than numbers. They represent a continuous international effort to hold Earth in a measurable relation to both the sky and the clock, a radio telescope in one hemisphere, a laser station in another, a navigation antenna on a quiet plain, and a timing laboratory far away all contribute to the same picture. Their observations move through correlators, analysis centers, combination centers, and official bulletins. By the end of that path, a tiny irregularity in the length of a day becomes a formal quantity that engineers, navigators, and astronomers can use. This is why the modern record of Earth's rotation is so convincing. The unusual behavior is not inferred from a single instrument or a single institution. It appears across a coordinated observing system that has been refined over decades. The world does not merely assume that Earth spins a certain way. It measures that spin against quasars, against satellite paths, against laser returns, and against atomic time itself. From those comparisons comes a quiet conclusion. The planet's rotation is never perfectly still in its rate, and the means of seeing that truth are among the most precise measurement systems that human science has built. The record of Earth's turning becomes especially striking when it is arranged as a sequence of days rather than as an abstract curve. For many decades, the daily changes are small enough to seem almost uneventful. The planet runs a little fast on one date, a little slow on another, and the differences remain buried inside fractions of a millisecond. Then the modern record reaches the early years of the present decade, and a distinct pattern begins to stand out. Since 2020, Earth repeatedly completes some rotations a little sooner than the standard day defined as 86,400 seconds. The change is tiny, but the repetition is unusual enough that scientists treat it as a real feature of the record rather than as random scatter. Before this recent run, the shortest day measured with atomic clock era precision remains about 1.05 milliseconds below the standard day. That older mark stands as a useful reference because it holds for many years. It suggests that fast days occur, but not beyond a certain narrow range. Then the pattern changes. In 2020, one of the year's shortest days falls in July and comes in about 1.47 milliseconds short. In 2021, another July day reaches a very similar value. In 2022, the record moves lower again, with a day about 1.59 milliseconds short. In 2023, the most extreme value of the year is less dramatic, but it still belongs to the same family of unusually brief days. In 2024, the sequence reaches its strongest point so far, when July 5th comes in about 1.66 milliseconds short of the standard day. In the scale of ordinary life, this is nothing at all, but in the scale of precision timekeeping, it is a clear shift. What gives the sequence its unusual character is not merely that one record is broken, it is the way the pattern persists across several years. The shortest day is no longer an isolated curiosity from a distant part of the record. It becomes a recurring event of the recent era. Scientists who compare the present with the previous half-century note that Earth is now producing slightly shorter days than was seen through much of that earlier period. The modern measurements therefore suggest a cluster of fast rotations concentrated in the years after 2020. That does not mean every day is shorter than average, and it does not mean the planet suddenly changes its long history. It means that the lower edge of the recent record drops to values not seen in the decades immediately before. The timing of these short days also has a visible rhythm. Many of the most extreme values fall around the middle of the year, often in late June, early July, or the weeks that follow. This seasonal placement does not make the pattern simple, because the exact dates change, and the amount of shortening changes as well. Still, when the years are laid side by side, the midpoint of the calendar begins to look like the part of the year where the fastest rotations are most likely to appear. The record does not present this as a perfect rule. It presents it as a tendency, one that becomes easier to notice as more recent years are added. By the time 2025 arrives, attention to the pattern grows wider. Reports focus on several dates in July and August, because calculations suggest that these may again be among the year's shortest days. Early expectations identify July 9th, July 22nd, and August 5th as likely candidates for especially brief rotations. As the season unfolds and updated estimates are examined, the exact ordering shifts slightly. Mid-August assessments indicate that July 9th, July 10th, August 5th, and August 6th all fall within a narrow band of very short days, with July 10th near 1.37 milliseconds short, and July 9th near 1.34 milliseconds short. August 5th and August 6th appear close behind, while July 22nd remains short but not as extreme in the refined estimate. Small revisions can change which date becomes the year's fastest spin. Even so, the main impression remains steady. 2025 continues the modern run of short days, but it does not clearly surpass the most extreme value seen in 2024. Some analysts therefore describe the year as a continuation, with a slight easing rather than a fresh plunge to a lower record. This nuance is important. The recent behavior is unusual, yet it is not a straight line moving in a single direction. Some years push farther, some pull back a little, and the curve remains irregular. The pattern is therefore best understood as a period in which Earth often rotates slightly faster than the earlier atomic clock record would have suggested. The size of these differences also deserves calm perspective. A millisecond is 1,000th of a second. Human senses do not register such a loss in the flow of an afternoon or the length of a night. No sunrise arrives early enough for the eye to notice, and no clock on a kitchen wall reveals the effect by itself. The change only becomes visible when many of the most stable clocks in the world are compared with measurements of Earth's orientation. Yet once it is measured, it is fully real. A short day in this context means that the planet completes one rotation relative to the Sun in slightly less than 86,400 seconds. The missing fraction is tiny, but it is not imaginary. What emerges from this sequence is a portrait of variability with a distinct recent character. The modern record does not show a planet keeping exactly the same pace from year to year. It shows a planet whose daily turning wanders within narrow limits, and whose lower limits become notably lower in the years after 2020. The shortest day of 2024 stands as the sharpest example so far. The closely watched days of 2025 show that the pattern remains active even if it may be easing. Taken together, these measurements form the observational heart of the current discussion. Earth is not racing in any ordinary sense. It is simply turning a little faster on some recent days than it did during most of the previous half-century, and modern instruments are steady enough to see that quiet change with certainty. Once the measurements are made and combined, they enter a quieter world of notices, bulletins, and carefully chosen language. This is where the changing rotation of Earth becomes an official public fact. The body most closely associated with that role is the International Earth Rotation and Reference System Service, known as IERS. Its task is not to create time, and not to control the planet, but to compare the rotation of Earth with the time kept by atomic clocks, and to state, in exact terms, how closely those two remain aligned. The clearest expression of that responsibility appears in a series of formal bulletins. Each one served a different purpose. Bulletin A provides rapid estimates and short-term predictions of Earth orientation parameters. These include the motion of the pole and the quantity called UT1 minus UTC, which gives the current difference between the time defined by Earth's actual rotation and the civil timescale used across the world. Bulletin B provides final values after a longer period of analysis and checking. It is calmer and more settled than Bulletin A, and it becomes part of the lasting scientific record. Bulletin D announces the value called DUT1, a rounded version of UT1 minus UTC that can be distributed with time signals for operational use. Bulletin C has the most public attention, because it announces whether a leap second will be introduced. These bulletins are not written in dramatic language. Their tone is spare, administrative, and exact. That style matters. Earth's rotation can sound mysterious when described in headlines, but the official notices treat it as a measurable geophysical quantity. A small change in the length of day is not framed as a threat or a surprise in itself. It is framed as a number, an observed difference, or a decision about whether the civil clock requires adjustment. The bulletins therefore act as a filter between the complexity of the planet and the practical needs of institutions that rely on time. Bulletin C is especially simple in form. It is issued at intervals of about 6 months, timed around the only moments when a leap second can be inserted under the present system, the end of June or the end of December. The bulletin either announces that a 1-second step will occur or states that no step will occur. It also repeats the standing difference between International Atomic Time and Coordinated Universal Time. Since the beginning of January 2017, that difference remains 37 seconds. This number does not mean that everyday clocks are off by 37 seconds from the sun. It means that UTC, which stays close to atomic time, stands 37 seconds behind the uninterrupted atomic scale known as International Atomic Time because of all leap second adjustments that have accumulated over the years. The pattern of recent announcements is quiet. No leap second has been introduced since the positive leap second at the end of December 2016. Bulletin C continues to state, half year after half year, that no leap second will be added at the next possible date. The current official notice says that no leap second will be introduced at the end of June 2026. This is the sort of statement that arrives without drama. Yet behind it lies the full chain of observations, calculations, and standards that connect radio telescopes, atomic clocks, and global timekeeping practice. The wording of these notices reveals an important feature of the system. A leap second is not scheduled far into the future as a matter of long-range planning. It is decided near the relevant date, after the behavior of Earth's rotation has been observed and compared with the civil timescale. This reflects the fact that UT1 does not move with perfect predictability. Tidal friction sets a long background tendency, but shorter variations can push the rotation slightly faster or slightly slower over periods of months or years. Because of this, the official process stays responsive rather than fixed. It waits, measures, predicts within limits, and then announces. Bulletin A supports that process by publishing current estimates and predictions for those who follow Earth rotation closely. Bulletin A provides the changing value of UT1 minus UTC as a living quantity rather than a historical one. This allows laboratories and technical users to see whether the difference is growing or shrinking, and how close it is to the threshold that would eventually require a time step. Bulletin B then confirms what the values truly are after more complete analysis. Bulletin D translates the refined knowledge into a practical signal for systems that need a simple broadcast correction. Bulletin C stands at the end of this chain and turns measurement into public timing policy. There is a calm discipline in the way these bulletins separate observation from decision. Bulletin A does not itself declare a leap second. Bulletin B does not dramatize the recent pattern of short days. Bulletin D does not attempt to explain the physics of the atmosphere, the oceans, or the deep earth. Each document remains inside its purpose. Together they form a layered language for describing Earth's rotation, with enough precision for science and enough stability for infrastructure. This division of roles is one reason the system has remained trusted across so many countries and technical fields. The official notices also make clear that civil timekeeping is a managed compromise. UTC does not follow every small fluctuation in Earth's spin from one day to the next. That would make the clock unstable and difficult to use. Instead, UTC runs with the steady atomic second and allows a small difference from UT1 to build until a rare adjustment becomes necessary. The bulletins track that difference continuously, while keeping the visible timescale smooth for most users. This arrangement accepts that Earth is variable while preserving the regularity that modern systems require. In recent years, the absence of new leap seconds becomes notable because it persists through a period when Earth often rotates slightly faster than many earlier decades would suggest. Yet the bulletins themselves remain unemotional. They do not speak of a rapidly changing planet in broad terms. They say only what is needed. No leap second will be introduced. The last leap second was positive and occurred at the end of December 2016. The difference between atomic time and UTC remains 37 seconds. UT1 minus UTC continues to be observed and published. These plain statements hold an entire planetary story within them. What emerges from this official layer is a picture of patience. Earth turns with small irregularities. Observers measure them. IERS publishes them in different forms for different needs. Civil time remains steady until the evidence requires otherwise. The bulletins do not remove uncertainty, but they contain it within a disciplined process. In that process, unusual behavior does not become real because it feels unusual. It becomes real because it appears in the official record expressed in numbers, dates, and a sentence that quietly tells the world whether the clock will step or remain as it is. A positive leap second is already an unusual event in modern timekeeping, but it belongs to the known world. It adds one labelled second to the end of a selected day. The clock shows 23 hours, 59 minutes, and 60 seconds before moving to midnight. This has happened before, and although it can be awkward for some technical systems, it exists inside long practice. A negative leap second belongs to a different category. It is part of the official rules, yet it has never been used. If one were applied, the clock would move from 23 hours, 59 minutes, and 58 seconds directly to midnight. One labelled second would be omitted. A minute would contain only 59 seconds. This possibility matters because the recent pattern of slightly shorter days raises the chance, at least in principle, that UTC could someday need to move in this direction rather than the older familiar one. For many years, the basic story of Earth rotation suggests slow, long-term braking. Tides raised by the moon and the sun gradually drain rotational energy, so the broad historical trend points toward longer days and the occasional need to add a second. That background remains true. Yet the modern record also shows shorter-term departures from that trend. During the recent run of fast days, the difference between UT1 and UTC can shrink in a way that makes a negative correction part of serious planning rather than a purely theoretical edge case. What makes the negative leap second unusual is not only that it has never happened, it is also unusual because the technical culture built around time distribution grows up around a different expectation. Many systems either ignore leap seconds, handle them in inconsistent ways, or only know how to accommodate the positive kind. In some implementations, a positive leap second is represented by repeating the final second of the day. In others, the extra second is spread over a longer interval by slightly slowing or speeding the clock, a method often called smearing. Some systems handle the event cleanly, others do not. A negative leap second would expose these differences in a new way, because skipping a labelled second is not simply the mirror image of repeating one. Software, hardware, and network protocols may all respond differently when asked to move from 58 to midnight with no 59 in between. This is why a negative leap second is often described as unprecedented. The word does not mean impossible. It means untested in operational civil time. Since the leap second system begins in the early 1970s, every leap second inserted into UTC has been positive. The procedures, workarounds, and habits that surround leap seconds therefore develop under one-sided experience. A system that claims to support leap seconds may in practice support only the kind that adds a second. The unfamiliar case creates a concern not because science doubts the concept, but because infrastructure may fail in uneven ways when confronted with a rare timing event it has never seen before. The issue grows larger because the modern world depends on distributed time. Financial systems stamp transactions in sequence. Power networks align monitoring and control data across large territories. Satellite navigation systems relate signals to exact epochs. Telecommunications networks maintain synchronization so that streams of information remain ordered. Scientific observatories combine data gathered at distant sites. In such settings, the clock is not merely a display. It is a coordinating signal shared across many machines and institutions. A 1-second discontinuity, even when announced in advance, can expose assumptions built deep inside code and firmware. If that discontinuity takes a form never previously realized, the risk becomes less familiar and harder to test against lived history. For this reason, the recent discussion around negative leap seconds connects naturally with a broader institutional move away from the leap second system itself. In 2022, the General Conference on Weights and Measures decides that the allowed difference between UT1 and UTC will be increased in or before 2035. The purpose of that decision is to preserve UTC as a continuous timescale for modern applications while keeping a formal relation to Earth rotation through a larger tolerance. The detailed implementation is left for further consultation and later agreement, but the direction is clear. Instead of continuing to interrupt UTC with rare 1-second steps under the old narrow limit. The international system prepares for a future in which UTC remains continuous for much longer spans. This change does not mean Earth rotation stops mattering. It means the relationship between civil time and planetary rotation is managed differently. Under the existing leap second system, the difference between UT1 and UTC is kept within less than 1 second. Under the future arrangement, that tolerance will become larger. The exact new maximum is still subject to international agreement, but the aim is continuity. Civil time would then remain smooth for far longer. while the growing difference from Earth rotation would be published and used where needed rather than corrected by sudden 1-second steps. The Sun would still cross the sky, and Earth would still turn with slight irregularities. The clock would simply stop trying to mirror every accumulated fraction at such short intervals. In this setting, the negative leap second becomes both a practical problem and a deadline. If the current rules remain in force long enough during a period of unusually short days, the world could face the first ever need to remove a second from UTC. That prospect has been serious enough to prompt dedicated workshops and formal discussion among the bodies responsible for standards and timekeeping. The concern is not only scientific prediction, it is resilience. Institutions must ask whether software, protocols, and operators across the world can handle an event that the standards permit, but experience has never tested. The idea of removing a second also carries a certain conceptual strangeness. A positive leap second feels like an insertion, a brief pause added to keep the civil clock aligned with the sky. A negative leap second feels like an absence, a missing label in the final minute of a day. The clock does not linger. It advances over a name that would ordinarily appear. For human awareness, this passes invisibly. No one senses the omission in daily life. For technical systems, however, a missing label can matter more than an added one, because sequence checking, logging, and interval calculations may rely on assumptions about which seconds must always exist. What emerges from this moment in timekeeping is not panic but transition. The older leap second framework still exists, and the negative case remains possible under its rules. At the same time, international standards bodies are preparing a different future in which UTC remains continuous, and the pressure to face a first negative leap second is reduced or removed before the deadline arrives. The present, therefore, holds two realities together. One is the unprecedented possibility of subtracting a second from civil time. The other is the growing decision that civil time may soon stop using leap seconds at all. Between these two realities lies the current meaning of the unusual. It is not that time itself becomes unstable. It is that the world's chosen way of reconciling atomic precision with the turning Earth reaches a point where an old system begins to give way. Far outside the atmosphere, the Moon and the Sun shape Earth with forces that are steady and unavoidable. Their gravity does not only guide orbits, it also pulls unevenly on the planet, stretching it slightly and raising tides in both ocean water and solid rock. These tides are not merely a rise and fall along coasts. They are a global deformation, a repeating response of the Earth system to changing gravitational stress. A tide begins with a difference. Gravity is stronger on the side of Earth closer to the Moon than it is at Earth's centre, and it is weaker on the far side. The same pattern exists for the Sun, though the Moon has the stronger tide-raising effect because it is much closer. The result is a pair of broad bulges, one facing the Moon and one facing away. In an ideal world with instant response and no friction, those bulges would sit exactly along the line connecting Earth and Moon. Earth, however, rotates, and real materials resist rapid reshaping. Friction within water, friction at the sea floor, and internal friction within rock all delay the response. The bulges are carried slightly ahead of the Moon's position by Earth's rotation. If there were no delay at all, the geometry would be perfectly symmetric, and there would be no sustained braking. The Moon would pull on the bulge, but the pull would point through Earth's centre, producing no net twist. The small offset breaks that symmetry. It turns the tide from a passive distortion into a mechanism that can exchange motion. In the ocean, the response is not a simple stationary hump. It is a moving pattern of long waves guided by continents and ocean basin shapes. In some basins, tidal waves can resonate, meaning their natural sloshing periods align partly with the tidal forcing and amplify currents and height changes. Where currents are strong and shallow water is common, friction and turbulence increase, and more rotational energy is converted into heat. That small offset is the heart of a slow break. The Moon's gravity pulls backward on the leading bulge. Earth's gravity pulls forward on the Moon. These paired pulls form a torque, a turning influence that transfers angular momentum between the rotating Earth and the orbiting Moon. Angular momentum is the quantity that describes how much rotational and orbital motion a system carries, and how that motion is distributed. In this exchange, Earth loses a small amount of rotational angular momentum, and the Moon gains a small amount of orbital angular momentum. Energy is dissipated as heat through turbulence and friction. So the process does not simply reverse when the geometry changes. Over long spans of time, the consequence is clear. Earth's rotation slows, and the length of the day increases. The Moon's orbit expands, so the Moon slowly moves farther away. This is not a drift that changes the sky in a lifetime, yet it is measurable. Laser ranging to reflectors on the Moon indicates an average increase in distance of a few centimeters per year. The rate varies over time and is influenced by the details of tidal dissipation, but the direction of change is well established. The slowing of Earth's rotation is also well established, though its pace is not perfectly constant. On very long time scales, the average lengthening is often described as being on the order of a few milliseconds per century. This background tendency does not mean every century is identical. The continents shift, the shapes of ocean basins evolve, and sea level changes alter how tidal energy is lost. When coastlines change, the areas of shallow water change, and the locations where tides dissipate most strongly can migrate. The Sun participates in the same basic mechanism, raising tides that also dissipate energy, but the lunar contribution remains dominant for the exchange that gradually lengthens the day. Evidence for this long-term change does not rely on modern instruments alone. Geological records contain rhythms that reflect ancient tides and seasons. In some sedimentary layers, thin repeating bands form as tidal cycles interact with longer cycles, leaving patterns known as tidal rhythmites. In some fossils, growth structures can preserve daily and yearly rhythms. When these natural archives are interpreted with care, they suggest that in the deep past the day is shorter and the year contains more days, meaning Earth rotates more times during one orbit around the Sun. Such reconstructions carry uncertainty because records can be incomplete and local conditions can alter growth or deposition. Even so, the broad picture aligns with physics. Tidal friction drains rotational energy, and over hundreds of millions of years it leaves a detectable imprint. The braking effect is gentle but persistent. Every tide involves motion, and motion in real fluids and real solids loses energy. Ocean tides generate currents that rub against the seafloor and coastlines. Waves break and create turbulence. In shallow seas, friction is strong, and the conversion of orderly motion into heat can be efficient. Solid Earth tides flex the crust and mantle by small amounts, and internal damping turns part of that flexing into heat as well. The energy does not vanish, but it shifts into forms that no longer support the steady spin of the whole planet. The rotation of Earth supplies much of the power that keeps the tidal system moving, and that power source implies a gradual loss of rotational speed. Within this outer gravitational region, uncertainty remains in the details rather than the fundamentals. The magnitude of dissipation depends on ocean depth, basin shape, coastline geometry, and the roughness of the seafloor, all of which change as Earth evolves. Even today, dissipation is not evenly spread. Some regions concentrate tidal energy and convert more of it into mixing and heat. Because these patterns can change, the long-term rate of slowing is not perfectly uniform. What remains certain is that the gravitational partnership of Earth, Moon, and Sun applies a persistent torque, and that this torque, filtered through friction, gradually reshapes both the length of the day and the distance to the Moon. The gravitational pull that slows Earth over long spans does not act with the same strength in every moment. The Moon moves along an orbit that changes in distance, tilt, and orientation, and these changing geometries reshape how strongly tidal forces can twist the planet. The effect is subtle, and it becomes visible only in careful measurements, yet it follows clear patterns. When the Moon's position changes, the pattern of tidal deformation changes, and the torque that transfers angular momentum varies with it. Earth therefore experiences a gentle modulation of its rotation rate that follows the Moon's shifting path. The most direct geometric change is distance. The Moon's orbit is slightly elliptical, so it comes nearer at perigee and farther at apogee. The tide-raising force depends on how rapidly the Moon's gravity changes across Earth's diameter, and that gradient is stronger when the Moon is closer. When the Moon is nearer, the tidal deformation it drives is larger. When the Moon is farther, the deformation is smaller, because the braking torque is linked to the size of this deformation and to the friction that accompanies it. The strength of the lunar braking effect is not constant through the month. The distance cycle supplies a regular rise and fall in the forcing that can be traced in the background of rotation data. Another important geometric change is direction relative to Earth's equator. The Moon's orbit is tilted relative to Earth's equatorial plane, and the Moon's track in the sky shifts north and south. This north-south angle is lunar declination. When declination is small, the strongest tidal bulges lie closer to the equatorial region. When declination is large, the bulges shift toward higher latitudes. This redistribution matters because the effectiveness of a torque depends on leverage around the rotation axis. A deformation closer to the equator interacts with the spin in a more direct way than an otherwise similar deformation closer to the pole. The Moon's changing declination therefore modulates how efficiently its pull can exchange angular momentum with the rotating planet. Declination also shapes the timing pattern of tides. A moon near the equatorial plane tends to favor a more even twice-daily rhythm in many places, because the two main bulges sweep past with similar geometry. A moon at higher declination tends to increase inequality between successive tidal highs, because one bulge passes closer than the other. This changes the way tidal forces are distributed around Earth over the course of a day. The pathway from that distribution to a change in the length of day depends on the full Earth system response, including the way oceans and rock deform and dissipate energy. Still, the geometric driver remains simple. The Moon changes latitude in the sky, and the strongest tidal pull shifts with it. These monthly changes sit inside longer lunar cycles. The plane of the Moon's orbit is not fixed. The line of nodes, where the Moon's orbit crosses the plane of Earth's orbit around the Sun, slowly precesses. This nodal cycle lasts about 18.5 years. As it progresses, the maximum lunar declination changes. In some years, the Moon reaches farther north and south. In other years, its range is more limited. This slowly alters the envelope of tidal forcing. It changes how often the strongest bulges are displaced toward higher latitudes and how often they stay nearer the equator. In rotation records, This cycle contributes to predictable variations on the scale of years, layered on top of shorter oscillations. The Moon's distance cycle also has a slower modulation because the orientation of the ellipse precesses. The line connecting perigee and apogee turns gradually in space, changing which lunar phases occur near closest approach. When perigee aligns near new moon or full moon, lunar and solar tidal forcing combine more strongly, producing larger tidal deformation than distance alone would imply. When perigee aligns near the quarter phases, the combined forcing is weaker. This is another example of geometry shaping intensity. It is not the result of a change in the Moon's mass or a change in Earth's internal structure. It is the result of moving angles among Earth, Moon, and Sun. At shorter timescales, the phase relationship between Moon and Sun produces the familiar spring and neap pattern. When the two bodies lie along a similar line relative to Earth, their tidal forces tend to add. When their directions are closer to right angles, the forces tend to offset. This creates a roughly 2-week modulation in the overall tidal deformation. In principle, stronger deformation and stronger friction lead to stronger torque exchange, and weaker deformation leads to weaker exchange. The resulting influence on Earth's rotation is small, but it is consistent enough to appear as a repeating component in high-precision records. Taken together, these geometries help explain why the length of day does not drift smoothly, even when the long tidal trend is steady. Earth does not receive the same twisting influence each day. Some days are associated with slightly stronger lunar forcing because the Moon is nearer, or because its declination places the strongest bulges in a more effective position, or because the Moon and Sun are aligned in a way that strengthens the tidal deformation. Other days are associated with weaker forcing. The differences are tiny. They do not transform the overall pace of the planet, but they do contribute to the day-to-day texture of the rotation record. This geometric framework also clarifies a limit. Celestial mechanics predicts the Moon's position, distance, and phase with great accuracy, so the timing of these cycles is well known. What is harder is to convert that geometry into an exact millisecond change for a specific date. The Earth system responds through moving water, moving air, and deformable rock, and those responses can amplify or reduce the geometric signal in ways that vary with season and with the evolving state of the planet. Observations indicate that lunar geometry is a reliable contributor to rotation variability. While it remains uncertain how large its share is on a given day compared with other influences, the Moon supplies a precise choreography in space, and Earth replies with a small but measurable adjustment in its turning, expressing that even the simplest external driver arrives with changing angles and changing strength. In the ocean, the pull of the Moon and the Sun becomes motion. The tide is not only a rise and fall along coasts, it is a global pattern of long waves that must fit into the shape of ocean basins and the blocking edges of continents. As that pattern moves, water presses against shorelines, pushes across continental shelves, and rubs along the seafloor. In these contacts, the ocean exchanges angular momentum with the solid Earth, leaving small traces in the length of the day. Two kinds of tidal motion help clarify what is happening. Some tidal flow is barotropic, meaning most of the water column moves together from surface to bottom as pressure changes sweep across a basin. Other tidal flow is baroclinic, meaning the tide interacts with density layering inside the ocean and generates internal waves that travel through the stratified interior. The first kind shapes the visible surface tide and the strong currents in shallow seas. The second kind is largely hidden from view, yet it carries energy away from coasts and into the deep ocean, where it can break and mix layers. Earth's rotation and basin geometry give tides their complex map. In many regions, the tide circulates around broad centers, forming amphidromic systems where the range is small near a nodal point and larger along surrounding coasts. Narrow straits, shelves, and shallow banks can accelerate flow, concentrating tidal currents into fast jets. The details differ from one basin to another, but the physical meaning is consistent. Moving water has inertia, and turning or slowing that water requires forces. Those forces act back on the solid planet. Friction is the key that turns tidal motion into a lasting influence on rotation. As currents sweep across a rough seafloor and through shallow channels, bottom drag and turbulence convert organized motion into heat. This energy loss must be replenished because the tidal forcing continues every day. Part of the replenishment ultimately comes from Earth's rotation, because the tidal bulges are slightly misaligned with the line to the Moon and the Sun, and are carried ahead by the planet's spin. The resulting torque transfers angular momentum out of Earth's rotation and into the orbital motion of the Earth-Moon system, while dissipation turns a share of that transferred energy into heat in the ocean. The same coupling appears on shorter timescales in a more reversible form. A tidal current that is accelerated by pressure gradients gains angular momentum. When that current is slowed by friction, it exerts a shear stress on the seabed and along coasts, and the seabed exerts an equal and opposite stress on the water, integrated over the globe. These stresses create small torques that can speed up or slow down the solid Earth by tiny amounts. The sign and size depend on the timing, the geography of the tide, and the changing lunar geometry described in the previous region. The ocean's own state modulates this exchange. Sea level and stratification change through the year, altering depths on shelves and the efficiency with which internal tides are generated. A slight change in depth can shift resonance in a bay or shelf sea, changing peak currents and energy loss. Stratification changes how easily the tide can lift and depress density layers over underwater ridges and slopes. When internal tides are generated strongly, energy can travel away as internal waves and then be dissipated far from the coast, mixing water masses and converting more tidal energy into heat. Beyond tides, the ocean contributes through large-scale currents that persist for months and years. These currents carry oceanic angular momentum, a measure of both moving water and the way water mass is distributed across the globe. When currents strengthen, weaken, or shift position, the ocean's angular momentum changes. Conservation then allows a compensating change in the rotation of the solid Earth. The effect is small, yet it becomes detectable when precision time records are compared with estimates of ocean motion. Mass distribution matters because Earth's rotation depends on the moment of inertia, the measure of how far mass lies from the rotation axis. When ocean mass is moved slightly toward lower latitudes, the moment of inertia increases and the day tends to lengthen by a small amount. When mass shifts toward higher latitudes or becomes more concentrated closer to the axis, the day tends to shorten. The ocean is thin compared with Earth's radius, but it covers most of the planet, so modest changes in sea surface height over wide areas can still shift mass enough to register faintly in rotation data. Storm surges and seasonal changes in sea surface height make this principle tangible. A surge piles water along a coast for a short time, redistributing mass until it relaxes. Seasonal warming expands the upper ocean and raises sea level in some regions, while cooling contracts it in others. These patterns are uneven because currents transport heat, and because the ocean responds differently in different basins. Each redistribution is temporary, yet each one nudges Earth's rotation and contributes to the background variability that sits beside the predictable tidal cycles. Within the observational record, the ocean's contribution is usually expressed as part of short-term length-of-day variability, often on the scale of a few tenths of a millisecond for seasonal and year-to-year changes. The long-term direction from tidal friction remains a break, but the shorter ocean signals can either lengthen or shorten the day, depending on how water is moving and where it is being stored. What remains uncertain is the exact share of a particular short day that belongs to ocean processes rather than to other parts of the Earth system acting at the same time. Ocean models and observations provide strong constraints, yet they still depend on seafloor roughness, coastal geometry, stratification, and limited sampling of currents and sea level. Within those limits, the ocean continues its steady work, turning the gravitational rhythm of the sky into moving water and leaving quiet, measurable fingerprints on the pace of the planet. Above the ocean and land, the atmosphere holds another moving layer of the planet. Air circulates around Earth under the influence of sunlight, rotation, and the uneven distribution of continents and seas. The winds that arise from these patterns carry angular momentum, the same conserved quantity that describes spinning and orbiting motion. When the atmosphere gains or loses angular momentum, the solid Earth responds with a matching change. The exchange is small, but it is measurable in the length of the day. Atmospheric angular momentum can be understood in two parts. One part comes from the mass of the air itself, because air has weight and it is distributed unevenly by pressure systems. When high pressure and low pressure patterns shift, the air mass shifts as well. The second part comes from wind, because moving air is mass in motion around the rotation axis. The wind contribution is often the larger driver of short-term changes in Earth's rotation, but both parts matter and both can interact. The exchange between atmosphere and solid Earth occurs through friction and pressure forces at the surface, and through pressure forces on mountains and large-scale topography. Near the ground, winds rub against land and sea surfaces. This friction slows the wind and transfers momentum to the surface. Over the ocean, friction is spread through waves and turbulent mixing in the air and the upper water. Over land, friction involves vegetation, rough terrain, and built structures. In addition, air pushes directly on mountain ranges, creating pressure differences that exert torques. Together, these processes allow the atmosphere to trade angular momentum with the planet's body. When the atmosphere's eastward motion increases, Earth's rotation tends to slow very slightly, lengthening the day. This is an expression of conservation. If air speeds up in the direction of Earth's rotation, it gains angular momentum. Unless an external torque supplies that gain, the solid Earth must lose an equal amount, so the planet's spin slows by a tiny amount. When the atmosphere's eastward motion decreases, Earth tends to speed up slightly, shortening the day. The sign of the effect therefore depends on whether the global circulation is carrying more or less eastward momentum than usual. Seasonal cycles provide a clear setting for this exchange. In one part of the year, the subtropical jet streams and mid-latitude westerlies strengthen and shift, and in another part they weaken or migrate. Monsoon circulations build and collapse, shifting wind patterns over wide regions. The global wind field therefore changes in a predictable seasonal way, and the length of day shows a seasonal pattern as well. In high-precision records, the seasonal cycle is one of the strongest recurring signals in length of day variability beyond the tidal components, with amplitudes commonly on the order of a few tenths of a millisecond. Shorter timescales also matter. Large weather systems move angular momentum around the globe in days. When strong westerly winds surge in one belt, they can create a temporary increase in atmospheric angular momentum. When those winds relax or shift, the angular momentum drops. These changes can produce day-to-day variations in the length of day of a few hundredths to a few tenths of a millisecond. The effect is small, yet it is not random. It corresponds to real changes in the global wind field. A well-known mode of atmospheric variability that influences these exchanges is the El Niño Southern Oscillation. In El Niño conditions, the tropical Pacific sea surface warms in characteristic patterns, and the atmosphere responds with shifts in convection, pressure, and winds. In La Niña conditions, the patterns shift in the opposite direction. These changes propagate through global circulation, affecting jet streams as storm tracks. As the winds reorganize, atmospheric angular momentum changes, and the length of day can shift accordingly. The connection is not constant in time, and it depends on the details of each event, but observations and models indicate that major El Niño and La Niña episodes can leave recognizable signals in Earth rotation. Another atmospheric process that influences the exchange is the quasi-biennial oscillation, a slow reversal of winds in the tropical stratosphere that occurs over roughly 2 to 3 years. Although this oscillation is higher than the weather of the troposphere, it interacts with wave motions and can influence broader circulation patterns. Its direct effect on Earth's rotation is smaller than that of the lower atmosphere, yet it forms part of the complex set of signals that appear in long records. Air pressure patterns also contribute through the mass term. When pressure increases over one region and decreases over another, the mass distribution of air shifts. This alters the moment of inertia of the atmosphere relative to the rotation axis. A mass shift toward lower latitudes tends to increase the moment of inertia and lengthen the day slightly, while a shift toward higher latitudes tends to shorten the day slightly. Because pressure systems move and reorganize. This mass term adds another component to length of day variability, often correlated with wind changes but not identical to them. The strength of the atmospheric contribution becomes especially evident when measurements are compared with atmospheric reanalyses. A reanalysis is a global reconstruction of atmospheric state produced by combining many observations with a physics-based model. Reanalyses estimate winds, pressure, and other fields day by day. From these fields, atmospheric angular momentum can be computed. When those computed changes are compared with observed changes in the length of day, the agreement is often strong for the timescales where the atmosphere dominates. This gives confidence that much of the short-term rotation variability is explained by the moving air above the surface. Still, uncertainty remains in the exact partition of causes for a particular very short day. The atmosphere, ocean, and other parts of Earth can act together, and their signals can overlap. In addition, the atmosphere is influenced by the ocean, by land surface conditions, and by the slow background warming of the climate system, which can shift circulation patterns in ways that are difficult to separate from natural variability. Observations indicate that the atmosphere can account for a large share of length of day changes on seasonal and shorter timescales, while it remains uncertain how much of the recent cluster of record short days is driven by atmospheric conditions versus other influences acting at the same time. Within this region of moving air, the main point stays simple. The winds are not merely weather at the surface. They are a spinning shell of mass wrapped around the planet. When that shell speeds up or slows down, the ground beneath responds, and the response appears as a faint change in how quickly Earth completes its daily turn. The atmosphere therefore connects the immediate variability of climate and weather to the precise measurement of planetary rotation, showing that the unusual can be as quiet as a shift in wind belts measured in a fraction of a millisecond. On land, water moves in slower, heavier ways than air. It gathers as snow, sinks into soil, fills rivers, and lies in underground stores that can persist for years. Each migration changes where mass rests on the spinning planet, because Earth's rotation depends on how its mass is distributed relative to the spin axis. These movements can slightly lengthen or shorten the day, and can also shift the position of the rotation axis in space. The basic physical link is the moment of inertia. When more mass sits farther from the rotation axis, the moment of inertia increases and the rotation rate tends to decrease, lengthening the day. When mass moves closer to the axis, the moment of inertia decreases and the rotation rate tends to increase, shortening the day. Land water is a thin layer compared with Earth's radius, but it is dense and it can cover immense areas. A change of a few centimeters of water stored across a continent can represent a very large mass shift when integrated across the area. Seasonal snow is one of the clearest examples. In winter, snow accumulates over high latitudes and mountain regions. Snow is water stored on land rather than in the ocean, and it often gathers in places that are not symmetric around the rotation axis. In spring and summer, that snow melts and runs toward rivers and ultimately toward the sea. As it melts, the mass distribution changes. The transfer of water from land to ocean tends to move mass toward lower latitudes, because the ocean spreads widely around the equator compared with high-latitude snowfields. That shift can increase the moment of inertia and slightly lengthen the day. In autumn and winter, the process reverses as precipitation and cold restore land storage. The seasonal cycle of snow and melt therefore contributes to a seasonal component in Earth rotation, adding to the seasonal signal already driven by the atmosphere and ocean. Soil moisture works similarly but with different timing. After a wet season, water infiltrates soil and is held in pores and layers. After a dry season, evaporation and plant uptake reduce that storage. Soil moisture changes can span large regions, particularly in monsoon climates or in areas influenced by persistent drought. Because the water is stored at specific latitudes and longitudes, the resulting mass distribution is uneven. When a region dries, water leaves the land and often returns to the ocean through river flow or atmospheric transport followed by precipitation elsewhere. When a region wets, mass accumulates. Each shift moves the center of mass slightly and alters Earth's rotation and axis orientation by small amounts. Groundwater is a deeper store, often slower to respond. Water can persist for many seasons or many years in aquifers, moving gradually through permeable rock and sediment. In natural conditions, groundwater is replenished by rainfall and lost by discharge to springs and streams. In modern conditions, pumping can withdraw groundwater faster than it is replenished. When groundwater is removed and used for agriculture or cities, much of it eventually reaches rivers and the ocean, either through runoff, drainage, or wastewater. The net effect is a long-term transfer of mass from land storage to the ocean. This transfer can influence sea level, and can also influence Earth rotation through mass redistribution. The influence on the length of the day from land water is typically small, often on the scale of hundredths to a few tenths of a millisecond. But it is measurable. It becomes clearer when Earth orientation data are compared with estimates of land water storage from satellite gravity missions and hydrological models. Satellite gravimetry measures tiny changes in Earth's gravitational field, which reflect changes in mass distribution. When these gravity changes are interpreted as shifts in water storage, they can be linked to changes in Earth's moment of inertia and to the observed rotation variations. This connection provides an independent line of evidence that the movement of water on land is not only a local environmental issue, it is a planetary mass signal. Land water also affects polar motion, the slow wandering of Earth's rotation axis relative to the crust. This axis motion is not the same as the tilt of Earth's axis relative to its orbit, but it is a shift in where the axis pierces the surface. When mass moves across the surface, the axis can adjust to conserve angular momentum. Large changes in land water storage, especially when persistent in time or concentrated in certain regions, can therefore nudge the axis and contribute to observed drifts and oscillations. The axis responds not only to water but also to air pressure, ocean mass changes, and internal Earth processes. Still, land hydrology can be an important piece of the overall signal. In this region, the word unusual can take a sober meaning. It can refer to persistent patterns of drought, intensified rainfall, changing snow cover, and large-scale groundwater depletion that alter the ordinary seasonal cycle of land water storage. A long drought can keep mass off the land that would normally return each year, while a sequence of wet years can do the opposite. Human water management can add additional long-term shifts. When reservoirs fill, mass is stored inland and can lengthen the day by a tiny amount. When reservoirs are drawn down, mass returns toward the ocean and can shorten it. When groundwater is pumped and not replenished, the land loses a store that once moderated seasonal swings. The influence of these factors on the recent record of very short days is not straightforward. Land water moves slowly compared with winds, and its effects overlap with atmospheric and oceanic contributions. Observations indicate that land water redistribution does contribute to variability in the length of the day and to polar motion. While it remains uncertain how much it contributes to specific record short days in the recent decade, the uncertainty does not come from doubt that water matters. It comes from the complexity of separating overlapping signals and from limits in observing land water with perfect global coverage and resolution. Within this layer of the story, the planet's rotation becomes sensitive to rivers that rise and fall, snowfields that build and melt, and underground reservoirs that quietly drain or refill. The shifts are too small for daily awareness, yet they are real enough to appear in the timing record. The ground is not only rock beneath the feet, it is also a moving distribution of water, and that distribution participates in the delicate balance that sets the length of a day. At the edges of the great ice sheets and across mountain ranges, ice moves in slow, heavy streams. Some of it remains stored for centuries, and some of it is now leaving the land and entering the ocean. This transfer is more than a change in scenery. It is a redistribution of mass across the planet. It alters sea level. It changes the loading of the crust, and it can influence Earth's rotation through the same principle that governs all mass movement on a spinning body. The long-term loss of land ice in Greenland, Antarctica, and mountain glaciers adds water to the ocean. The added water does not remain where it enters. The ocean spreads it around the world, and winds, currents, and gravity shape how sea level rises in different regions. From the perspective of rotation, the key feature is that water leaving high-latitude land ice tends to increase mass at lower latitudes when it becomes part of the global ocean. This shift generally increases Earth's moment of inertia and tends to slow rotation, lengthening the day by a very small amount. This is one reason scientists describe ice loss as a process that can oppose a period of short days rather than reinforce it. The effect is often compared to a skater changing posture. When mass is distributed farther from the axis, rotation slows, and when mass moves inward, rotation speeds up. Earth is not a rigid skater, but the analogy captures the direction. Meltwater moved from high-latitude ice sheets to the global ocean effectively spreads mass outward from the axis, because much of the ocean lies closer to the equator than the ice sources. The change is small, but the total mass involved is large. Over decades, the cumulative effect becomes measurable in the global accounting of mass distribution. This transfer also affects the position of Earth's rotation axis relative to the crust. When ice sheets lose mass in one region, the gravitational and rotational balance of the planet adjusts. The rotation axis can drift, and the crust can respond through deformation. A slow component of this response is glacial isostatic adjustment, the rebound of land once pressed down by the weight of ice. During the last glacial period, large ice sheets depress the crust, pushing mantle material outward. After the ice melts, the crust gradually rises and the mantle slowly flows back. This process continues today, long after the largest ice sheets of the last ice age retreat. It changes local land levels, it alters gravity, and it can shift how a mass is distributed inside Earth's outer layers. Modern ice loss adds a newer layer to this older adjustment. As present-day ice thins, the crust responds elastically first, bending upward slightly as weight is removed. Over longer periods, the mantle's viscous flow contributes additional rebound. These responses move mass within the solid Earth as well as on its surface. They can influence Earth's rotation and axis orientation, and they also affect regional sea level, because land motion changes the relative height between coast and ocean. The combined signal is therefore a blend of water added to the ocean, land rising or sinking, and mantle material moving slowly beneath. The net influence of modern ice loss on the length of day is generally toward longer days. This is a broad statement, and it sits on a foundation of models that account for how water is redistributed and how Earth deforms. The uncertainty lies in details, such as how quickly ice is lost in particular basins, how meltwater spreads in the ocean, and how strongly the solid Earth responds. Yet the direction remains consistent. Moving mass from polar land to a more equatorward ocean is a change that tends to increase Earth's moment of inertia. This creates an important contrast with the recent run of very short days. If the planet is losing ice and adding water to the ocean in a way that should, on average, lengthen the day, then the short-day cluster likely requires other influences to dominate on the relevant timescales. This does not remove the role of ice loss in Earth rotation. It places it within a balance of competing effects. Some processes push towards slightly shorter days, and others push towards slightly longer days. Ice loss belongs mainly to the latter group. Ice loss also influences rotation indirectly through its effect on sea level and on the distribution of ocean mass. Sea level rise is not uniform. When ice mass is removed from Greenland or Antarctica, the gravitational attraction those ice sheets exert on nearby ocean water changes. Nearby sea level can fall even as global mean sea level rises, because the reduced gravitational pull allows water to migrate away. Farther from the ice, sea level can rise more than the global average. This spatial pattern affects the mass distribution relevant for rotation. It also depends on Earth's rotation and shape, because the planet's equilibrium surface for the ocean is not a perfect sphere. These interactions are complex, but the general implication remains. The mass added to the ocean becomes part of a global redistribution that includes both gravity and rotation. Mountain glaciers contribute in a similar way, though each glacier is smaller. Taken together, their mass loss can be substantial. Their meltwater enters river systems and then the ocean. adding to the same general redistribution toward lower latitudes. Because mountain glaciers are spread across many latitudes, their rotational effect can be more mixed than that of polar ice sheets, but the net still tends toward increased ocean mass and a slightly larger moment of inertia. In this region, the scientific language remains careful about what is known and what remains uncertain. Observations indicate that land ice is losing mass and that the ocean is gaining it. Observations also indicate that Earth's rotation axis drifts and that the length of day varies on many timescales. Models and measurements together indicate that ice loss contributes to both, generally in a direction that lengthens the day. It remains uncertain how the competing effects from atmosphere, ocean circulation, land-water storage, and internal Earth processes combine to produce the exact modern pattern of very short days. The uncertainties do not mean the system is mysterious. They mean the system contains many moving parts that overlap in time and in magnitude. The quiet conclusion of this layer is that melting ice is a planetary redistribution. It shifts weight from land to sea, changes the loading of the crust, and slowly alters the balance of a spinning Earth. Even when its influence does not explain a recent acceleration, it remains part of the background against which that acceleration is measured. The ice, by leaving the land, becomes a small but persistent factor in the long-term accounting of Earth's rotation. Human activity moves water with an intention that natural cycles do not possess. Pumps lift groundwater from deep layers that once change slowly. Canals carry river water across divides. Reservoirs hold back seasonal floods and store water far inland. Cities concentrate consumption and return flow in predictable places. Each action is local in motive, yet the combined effect becomes large enough to appear in geophysical measurements of mass distribution and Earth orientation. A reservoir is among the clearest examples because it stores water as a visible mass placed on land. When a large dam closes and a valley fills, billions of tons of water gather behind a concrete wall. The surface rises, the shoreline expands, and the weight presses downward on the crust. From the perspective of rotation, the key is where the water is stored. If a reservoir lies far from the rotation axis, then storing water there increases Earth's moment of inertia and tends to lengthen the day by a tiny amount. When the reservoir is drawn down, the mass leaves that inland location and is redistributed through rivers in the ocean, tending to move mass away from the reservoir's latitude and toward a more global spread. The sign and size of the rotation change depend on the latitude of storage and on how the released water is distributed afterward. The effect of any single reservoir is usually small, yet the 20th century sees a rapid expansion of dam building, and the combined storage of many large reservoirs becomes significant. This cumulative storage can lower global sea level slightly, compared with a world without that water held on land. Because water that might otherwise reach the ocean remains trapped inland, in mass terms, it is a shift of water from the ocean's broad equatorial spread to more localized inland basins, often at mid-latitudes. This redistribution alters the moment of inertia and can influence Earth's rotation and the position of the rotation axis by small but measurable amounts. Reservoirs do not only store water, they also load the crust. The added weight bends the lithosphere, the stiff outer shell of Earth, and forces the underlying mantle to flow slowly in response. This deformation changes the shape of Earth slightly, and any change in shape is also a change in mass distribution. The elastic response appears quickly, while the viscous response takes longer. In rotation records, these adjustments are subtle, but they belong to the same family as the rebound that follows ice loss. The difference is that the timing and location are set by engineering and management rather than by climate. Groundwater pumping creates a different pattern because it removes stored mass from beneath land and eventually transfers much of it to the ocean. When groundwater is pumped and used, it can be evaporated by irrigation, transpired by plants, discharged as runoff, or released as wastewater. Over time, much of that water reaches rivers and then the sea. If pumping exceeds recharge, the land loses a store that does not quickly return. The net effect is a long-term shift of mass from continental interiors to the global ocean. This shift tends to increase Earth's moment of inertia and can lengthen the day, much like ice melt, while also contributing to changes in the rotation axis. The axis response is often easier to detect than the day-length response because mass shifts that are not perfectly symmetric can push the axis laterally. When groundwater is removed primarily from certain continents or basins, the loss is uneven. The ocean gain is also uneven at first, then becomes more widely distributed. The combination can contribute to observed polar motion, the wandering of the rotation axis relative to Earth's crust. In the measurement record, polar motion contains many influences, including atmosphere, ocean, and internal Earth processes. Yet the role of long-term hydrologic redistribution becomes clearer as satellite gravity data improve and as hydrological accounting becomes more detailed. Water management also moves mass seasonally through patterns that differ from natural timing. A reservoir can be filled or emptied according to human schedules that respond to power demand, irrigation cycles, or flood risk. A managed river can carry water later in the year than it would naturally, keeping mass stored upstream until release is chosen. Irrigated agriculture can add water to soils during a dry season that would otherwise be dry, shifting the seasonal cycle of land water storage. Each management choice leaves a small signature in how water mass is distributed through the year, and that signature can overlap with the seasonal signals driven by snow, rain, winds, and ocean currents. In some places, groundwater pumping also causes the ground itself to sink, a process called subsidence. When water pressure in an aquifer drops, sediment layers can compact. This changes the local elevation and changes the internal density structure of the near surface. Subsidence does not move large masses across the globe on its own, but it represents a rearrangement of the crust at local scale and a reminder that water removal can reshape solid Earth. Where subsidence is widespread, it can alter drainage and further change the path by which water returns to rivers and sea. In the broader accounting, human-driven water redistribution competes with natural variability. A wet year can refill reservoirs and raise soil moisture, while a drought year can empty storage and increase pumping. Climate change can alter these patterns, changing evaporation demand and shifting precipitation. Human response can amplify or damp those changes through additional pumping or altered reservoir operation. The resulting mass movement is therefore a blend of climate signals and management signals. In rotation observations, this blend becomes a challenge of separation. It can be clear that water redistribution contributes, while it remains uncertain how much of a particular short-term rotation change should be attributed to human water movement, rather than to natural hydrology or atmospheric circulation occurring at the same time. The unusual aspect of this region is the scale at which ordinary decisions accumulate. A single irrigation district, a single dam, or a single city does not alter Earth's rotation in an obvious way. Yet across decades, the combined transfer of water among aquifers, rivers, reservoirs, and the ocean becomes large enough to nudge measurable quantities such as polar motion. The planet responds not because it is fragile, but because it obeys conservation and geometry. Mass moved across latitudes and longitudes alters the moment of inertia and shifts the balance of a spinning body. In this layer of the story, the science stays grounded in observation. Satellite gravity reveals where mass is leaving land and where it is accumulating. Hydrological data reveal where pumping is greatest and where reservoirs store water. Earth orientation measurements reveal the axis motion and the subtle changes in day length. When these records are compared, a coherent picture emerges. Human redistribution of water is not only an environmental and economic story, it becomes a small geophysical force, measurable at planetary scale, and it joins the long list of processes that can make Earth's rotation appear slightly faster or slightly slower at different times. Beneath the moving air and water, the solid Earth responds in ways that are slower and quieter but still real. The crust and the uppermost mantle form a shell that looks rigid at human scale, yet it bends under changing loads. Under that shell, the mantle flows very slowly, behaving like a solid on short timescales and like a very viscous fluid on long ones. Together, these properties allow Earth to adjust its shape when mass is added or removed at the surface. Those adjustments alter where mass sits relative to the rotation axis, and they therefore influence the length of the day and the position of the rotation axis. The outer rock layers are often described in terms of the lithosphere, a strong layer that includes the crust and the uppermost mantle. The lithosphere is broken into plates that move over geological time, but it also behaves elastically on shorter spans. Elastic means it can deform under stress and then partly recover when the stress is removed. When a large mass is placed on the surface, such as an ice sheet, a lake, or a large reservoir, the lithosphere bends downward. When that mass is removed, the lithosphere bends upward. This bending is not an all-or-nothing event. It is a continuous response that begins immediately as the load changes. Below the lithosphere lies mantle material that can flow slowly under sustained stress. This flow is the basis of a process known as isostatic adjustment, the tendency of Earth to approach a state where the weight of columns of rock is balanced. When a heavy load presses down, mantle material is displaced and moves away. When the load is removed, mantle material flows back. This is not fast like water in a river. It is slow like thick material that yields over many years. The time scale depends on viscosity, a measure of resistance to flow, and on the thickness and strength of the layers involved. This coupling between elastic bending and viscous flow means that Earth's response to surface mass change has two phases. The first is immediate and elastic, and the second is delayed and viscous. When ice melts from a region, the land can rise quickly by a small amount, and then it can continue rising for centuries as the mantle gradually adjusts. When a reservoir fills, the land can sink slightly at once, and then it can continue settling as deeper material slowly responds. Both phases involve movement of mass. The surface load itself may be water or ice, but the rock beneath also shifts. That shift changes Earth's mass distribution in a way that can affect rotation. The rotational effect can be understood as a change in shape and a change in moment of inertia. When a region is loaded, the surface moves downward and the surrounding area can bulge slightly upward, spreading the deformation over a broad region. This is called flexure. Flexure changes where rock mass is concentrated. When a load is removed, the deformation relaxes in the opposite direction. If the net effect moves mass outward from the rotation axis, the day tends to lengthen. If it moves mass inward toward the axis, the day tends to shorten. The sign depends on the geography of the load and the details of Earth's response, but the principle remains the same. Rotation responds to where mass lies. Earth also responds through a change in its gravitational field and its figure, meaning its overall shape relative to the rotation axis. The planet is slightly flattened at the poles and bulged at the equator because it rotates. That equatorial bulge is a stable feature of the long-term balance between gravity and centrifugal tendency, yet it can be modified slightly by mass redistribution. When large amounts of mass move toward lower latitudes, the equatorial bulge can be reinforced in a tiny way, increasing the moment of inertia and lengthening the day. When mass moves toward higher latitudes, the opposite can occur. In practice, these figure changes are small, but they are part of the full accounting. The axis of rotation responds as well. Earth does not spin on an axis fixed to the crust. The rotation axis in space is determined by the distribution of mass and the state of motion of the whole planet. When mass shifts on the surface and within the shallow interior, the axis can move relative to the crust to maintain angular momentum balance. This is seen as polar motion, the slow wandering of the axis across the surface. Elastic deformation and viscous flow both contribute because they move mass, and because they change the way Earth resists rotation about different axes. One important source of ongoing viscous adjustment is the legacy of the last ice age. Large ice sheets once cover broad regions of the northern hemisphere, and their weight depresses the crust and displaces mantle material. After the ice retreats, the crust begins to rebound. Even today, some regions continue to rise, while surrounding regions can subside as mantle material returns. This ongoing adjustment is not driven by modern climate alone. It is a long memory in the solid Earth, and it continues to alter mass distribution and gravity. Its contribution to Earth rotation is part of the background signal that must be accounted for when scientists interpret present-day changes. Modern changes, such as present-day ice loss and large-scale water redistribution, add new loads and unloads to this already adjusting system. The solid Earth responds with its own timing. The elastic part follows closely. The viscous part lags, meaning that today's rotation signals can contain both the immediate response to recent mass change and the delayed response to older events. This overlap makes interpretation challenging. Observations indicate that the solid Earth's adjustment contributes measurably to long-term trends in Earth orientation, while it remains uncertain how large the contribution is to specific short-term clusters of record-short days, because those clusters unfold on timescales where atmosphere and ocean variability can dominate. The crust and mantle also respond to earthquakes and to the slow motion of tectonic plates, though these influences operate differently. A large earthquake can shift mass slightly by moving blocks of crust and by changing Earth's moment of inertia, producing a tiny change in day length. The effect is real but usually extremely small compared with daily variability, and it appears as a step-like change rather than a smooth seasonal pattern. Plate motion, on the other hand, rearranges continents over millions of years, changing ocean basin geometry and the distribution of mass, but it is too slow to explain the modern year-to-year pattern of short days. Still, these processes remind the observer that the solid Earth is not a fixed platform. It is an active body whose structure and shape evolve. Within this region, a key concept is coupling. The surface load does not act alone. When water accumulates in a basin, the crust bends. When water is removed, the crust lifts. When ice melts, the mantle flows. These responses change sea level locally and alter gravity, which then influences where water spreads. The system is connected. The rotational response is therefore not simply a direct consequence of moving water, It includes the delayed and distributed motion of rock as Earth seeks balance. Modern measurement systems can detect these adjustments. Networks of positioning stations track land motion, revealing uplift and subsidence over wide regions. Satellite gravimetry detects mass changes associated with both surface water and deeper redistribution. Earth orientation measurements track polar motion and length of day changes. When these records are compared, they show that the solid Earth's response is a necessary part of the explanation for long-term trends. It provides a slow structural context in which faster processes operate. The unusual aspect in this layer is not a sudden shift but the way solid rock participates in timekeeping. Earth's rotation is measured with atomic clocks, yet it is shaped in part by the yielding of a mantle material and the bending of the crust under changing loads. The planet's day is therefore connected to the slow mechanics of a layered interior. The crust and mantle do not merely support continents and oceans. They share in the redistribution of mass that changes how Earth spins, quietly turning surface climate and water movements into subtle adjustments of a rotating world. Deeper than the bending crust and flowing upper mantle lies a boundary that is not seen directly, yet it influences the whole planet. The mantle rests on a liquid outer core made mostly of iron with lighter elements mixed in. The boundary between them, the core-mantle boundary, sits thousands of kilometers beneath the surface. It is a place of sharp change. Rock above behaves as a very slow solid. Metal below moves as a fluid. Across this interface, Earth can exchange angular momentum in ways that appear in the length of the day over years and decades. The core does not rotate in perfect lockstep with the mantle. The entire planet shares a common mean rotation, yet the outer core can speed up or slow down slightly relative to the mantle. This relative motion matters because the core contains a large fraction of Earth's mass. If the core's rotation changes even a tiny amount, the angular momentum of the whole system changes unless an equal and opposite change occurs elsewhere. Conservation then implies that if the fluid core rotates a little faster, the solid mantle and crust may rotate a little slower. Lengthening the day, if the core rotates a little slower, the mantle and crust may rotate a little faster. Shortening the day, the exchange is small, but it can be large enough to explain some of the observed length of day variations on timescales longer than seasonal atmospheric and oceanic variability. The physical mechanism for this exchange is coupling across the core-mantle boundary. Several forms of coupling are possible. One involves pressure forces. The core-mantle boundary is not a perfectly smooth sphere. It has topography, meaning there are subtle highs and lows shaped by mantle convection and by the density structure near the boundary. As the core fluid moves, it can push on these irregularities, producing pressure torques that transfer angular momentum. Another form involves gravitational coupling. If density variations in the lowermost mantle and in the outer core align in certain ways, gravity can produce torques that resist relative motion and allow exchange. A third form involves electromagnetic coupling. The outer core generates Earth's magnetic field through the motion of electrically conducting fluid. That magnetic field threads into the lowermost mantle to a small degree. If the base of the mantle has electrical conductivity, then moving magnetic fields can induce currents and generate forces that couple core flow to mantle motion. The strength of this coupling depends on the conductivity structure and on the flow patterns in the core. In this deep region, the measurements become indirect. Scientists cannot place instruments at the core-mantle boundary. Instead, they infer core behavior from two kinds of observations. One is Earth rotation itself, expressed as changes in the length of the day and in the orientation of the rotation axis. The other is the geomagnetic field, measured at the surface and from satellites. Because the magnetic field is generated by core flow, changes in the field can carry information about the flow. When patterns of magnetic change are analysed, they can suggest how the fluid is moving at the top of the core and how that motion evolves over years. These inferences have revealed that core flow is not steady. It varies on a range of timescales. In some analyses, changes in the magnetic field are interpreted as waves or jets within the outer core, moving along lines set by rotation and magnetic forces. Some patterns resemble torsional oscillations, which are wave-like changes in the rotation of cylindrical shells of fluid aligned with the rotation axis. In such oscillations, bands of fluid speed up and slow down, and the changes propagate through the core. Because the core and mantle are coupled, these oscillations can exchange angular momentum with the mantle and appear as length-of-day variations. The timescales involved, often several years to a few decades, match some observed components of length-of-day change that are not fully explained by atmosphere and ocean alone. The link between deep core dynamics and day length is therefore a plausible and widely discussed part of Earth rotation science. It does not replace the effects of tides, winds, and water. It operates in a different band of time, one that becomes more important when seasonal signals are removed and when the remaining variability is examined over longer spans. In many studies, the length of day shows a decadal component that aligns with features inferred from geomagnetic observations, suggesting that core mantle angular momentum exchange contributes substantially at those scales. Yet uncertainty remains. The inference from magnetic field to core flow is not unique. Different flow patterns can sometimes produce similar magnetic signatures, and the mantle's conductivity structure is not known in perfect detail. The coupling mechanisms may vary in strength across regions of the boundary. Pressure coupling depends on the shape of the boundary, which is inferred from seismic studies but still has uncertainties. Gravitational coupling depends on density structures that are not fully mapped. Electromagnetic coupling depends on conductivity and on magnetic field structure. Observations indicate that the core and mantle do exchange angular momentum, while it remains uncertain exactly how that exchange is partitioned among these mechanisms and how it varies over time. This uncertainty becomes especially relevant when attention turns to a recent period of shorter days. Some scientists consider whether a change in core flow might contribute to a modern acceleration of the solid Earth's rotation. The reasoning is conservative. The core is capable of exchanging enough angular momentum to matter at millisecond levels over years. The magnetic field record shows ongoing change. Therefore, it is reasonable to ask whether core-mantle coupling plays a role in the recent behaviour. At the same time, the atmosphere and ocean also produce length-of-day variability, and their contributions can be large on the same timescales. Separating the deep signal from surface signals requires careful analysis. In the deep context, the word unusual can be understood as a shift in emphasis rather than a claim of novelty in nature. The outer core is always moving. It is a turbulent conducting fluid under strong rotational constraint. Its flow evolves, and the magnetic field evolves with it. The coupling to the mantle is a normal part of this system. What changes is the pattern and timing of the exchange, and the way modern measurement allows small shifts to be identified and discussed. This region also reveals a quiet unity in Earth science. The length of a day, a quantity that can be measured by a clock on a laboratory bench, connects to a flow of liquid metal thousands of kilometers below. The same planet that carries clouds and tides also carries a churning core and a magnetic field. The measurements that suggest a recent cluster of shorter days therefore point inward as well as outward. They invite consideration of the deepest moving layer that can exchange angular momentum with the surface. Within the limits of present knowledge, observations indicate that core mantle coupling contributes to length of day variability on year-to-decade scales. It remains uncertain whether recent short-day behavior requires a significant change in core rotation, or whether surface processes can account for most of it. What is clear is the existence of the pathway. A fluid core can speed up or slow down relative to the mantle, coupling through pressure, gravity, and electromagnetic forces, and the result can appear as a small change in the turning rate of the crust. The deepest moving region of Earth thus joins the surface layers in shaping the measured rhythm of time. At the deepest moving layer, the outer core, Earth's rotation is tied to motion that is both powerful and partly hidden. The core is a vast ocean of liquid metal, rotating with the planet while also circulating within it. Its flow maintains the geomagnetic field, and its changing patterns can exchange angular momentum with the mantle and crust. In recent years, the attention to slightly shorter days leads naturally to a question framed in careful scientific terms. The question is whether changes in the core's motion contribute meaningfully to the present pattern of faster rotation, and how that possibility can be assessed without overstating what the data can prove. The first point is the scale of what is being discussed. A change of about 1 millisecond in the length of day is a change of about 1 part in 100 million of the total day length. For the rotation of a planet, that is a small fractional change. Yet it is large enough to be measured clearly by modern systems. If such a change arises from the core, it does not require the core to suddenly change state. It would require only a very slight shift in how angular momentum is partitioned between core and mantle. Because the core carries a large share of Earth's moment of inertia, small relative changes can matter. Scientists investigate this possibility by comparing multiple records. One record is the time series of length of day variations, after known influences are accounted for as well as possible. Another record is the changing geomagnetic field. The geomagnetic field is measured at observatories and by satellites, and it is described by models that represent the field structure and its evolution. Because the field is generated by flow in the outer core, changes in the field can be used to infer aspects of that flow, especially near the top of the core. When inferred core flow shows accelerations or oscillations on certain timescales, researchers examine whether similar timescales appear in the length of day record. A long-standing result of this approach is the presence of decadal variability. Length of day does not only show seasonal changes driven by winds and water, it also shows slower oscillations, often around several years to a decade or two. These slower variations align in timing with some features of geomagnetic change, supporting the idea that angular momentum exchange with the core is a real driver at those scales. This does not mean the core controls day length in every period. It means that when the atmosphere and ocean signals are filtered out or averaged over longer spans, a deeper contribution can remain. The modern cluster of record short days, however, occurs on a shorter and more irregular timescale. It rises into attention after 2020 and produces prominent extremes in the middle of the year in several consecutive years. This temporal pattern overlaps with strong seasonal forcing and with the high variability of the atmosphere and ocean. In this setting, the core hypothesis becomes harder to test in a clean way. The core's influence is expected to be smoother and more decadal, though it can include shorter components such as torsional oscillations that might influence year-to-year behavior. The surface layers, by contrast, can change rapidly, and can produce short-term shifts in length of day that are comparable in magnitude. The challenge is therefore not to imagine a deep cause for every short day, but to estimate how much of the recent behavior can be explained by known surface exchanges and how much remains as a residual that might plausibly point inward. In careful studies, the atmosphere often accounts for much of the short-term variability. The wind field changes day to day and season to season, and these changes can be translated into predicted length of day variations using angular momentum budgets. The ocean adds its own contributions through tides, currents, and mass redistribution. Land water adds seasonal loading and longer changes. When these components are combined, a large fraction of observed variability can be reproduced. Yet no model captures every detail. Uncertainty persists in wind analyses, in ocean circulation estimates, in hydrological storage, and in how these systems interact. Even when the broad match is good, residuals remain. These residuals do not automatically imply the core is responsible. They can arise from limits in observing and modeling the surface systems. They can also arise from the way multiple processes overlap, sometimes reinforcing and sometimes cancelling each other. A day that appears very short may occur when several processes align in the same direction, such as a temporary drop in atmospheric angular momentum combined with a particular ocean mass distribution and a lunar geometry that alters tidal torque. In such a case, the explanation can be largely within the surface and near-surface layers. The core may still be exchanging angular momentum in the background, but it may not be the dominant trigger of the most extreme daily values. At the same time, it would be too narrow to exclude the core from consideration. The core's angular momentum exchange is real, and the length of day record contains components consistent with it. The geomagnetic field continues to change, and it sometimes shows accelerations or shifts that suggest changing core flow. It is therefore scientifically reasonable to treat the core as part of the complete set of influences on Earth's rotation, especially when the goal is to understand year-to-year variations and multi-year episodes rather than individual days. The present evidence indicates that core-mantle coupling contributes to longer-term variations, while it remains uncertain whether it makes a major contribution to the specific modern acceleration that produces the recent record short days. This uncertainty is not a failure of measurement. It is a reflection of a system with multiple moving layers. Earth is a coupled body. Air moves and exchanges momentum through friction and pressure. Water moves and exchanges momentum through tides and currents. Land water shifts and redistributes mass. Ice melts and alters loading and sea level patterns. Rock bends and rebounds. Deep metal flows as generates the magnetic field. Each process has its own characteristic timescales and amplitudes, and the observed rotation is the sum of their interactions. Within this deepest region, the narrative becomes a disciplined statement about what is known. Observations indicate that Earth's rotation varies by fractions of a millisecond from day to day and by larger amounts over seasons and decades. Observations indicate that the outer core's flow varies and that core-mantle coupling can exchange angular momentum. Models indicate that the atmosphere and ocean explain much of the short-term variability, and that the core contributes at longer time scales. It remains uncertain how much of the recent cluster of very short days reflects a deep change in core dynamics versus a combination of surface and near-surface factors. The uncertainty is bounded. It does not suggest the planet behaves without rules. It suggests that the full accounting requires continued measurement, improved models, and careful separation of overlapping signals. The practical meaning of this deepest layer returns to the beginning. to civil time. The possibility of a negative leap second and the broader move away from leap seconds are not driven by a sudden danger in Earth's interior. They are driven by a measured drift between atomic time and Earth rotation, and by the need to keep global systems stable. The deep core may be one contributor to that drift over certain spans, but the management of civil time is a human response to measured variability, not a response to a single hidden event. The outer core remains out of sight, yet it is present in the rhythm of the day. The planet turns with a pace that is not perfectly constant, because the planet is not a single rigid object. It is a layered body exchanging motion among its parts, from the moon's tidal pull to the winds, from melting ice to flowing metal. The unusual, when described with care, is the recognition that Earth's time is not only counted by atoms, it is also carried by a rotating world whose layers continue to move.